there's kind of two levels to this class. There's the formulas and the numbers and putting everything in the right place. And then there's the idea behind everything. And this is the class where some classes you can get away without understanding a damn thing. You just know, when I see this, I do this, and I get this, and there you go. I do this, and this, and this, and there you go. This class is really difficult to do that. It's really hard to get away with that in this class. And that's what makes it difficult. I told you that first day. There are no word problems. It's the concepts that really make this class difficult. So what we're getting into now is sort of like what I had up here on the board a minute ago. Standard deviation, and again, what's the difference between these two symbols here? Like, so the Greek is always the population, standard deviation, and this is a sample standard deviation. Well, whatever it comes from, the standard deviation is the benchmark that I use to measure distance when I'm dealing with data. Right? So if I was comparing how much money billionaires make, would a difference of $15 really matter? Like if one year I made $4 billion and $15, and the year before I made $4 billion, I basically made the same amount of money. You with me? You with me? Yeah. But if I'm talking about some country where they don't make anywhere near that much money, so one year I made $7 for that year, and the next year I made $22. That's a difference of 15. How important is it then? That's huge. Holy crap, you more than tripled the amount of money you made. You with me? Hopefully things don't cost a lot there. So those are things that we intuitively know. We kind of intuitively compare it to in the right way. When I have data that doesn't really change that much, the standard deviation is going to be smaller. Right? And what I really mean by that is when I have data like 4 billion, 5 billion, 6 billion, my standard deviation is going to be on the order of billions there, right? So it kind of adjusts itself to match what the data itself is doing, so I can see how far apart things really are. 4 billion and 5 billion aren't really that far apart. Let me do this. If I have 4 billion as one data point, and 5 billion is another, but my standard deviation is 1 billion, are these very far apart? No, they're not. You could say, one person would say, before we get into this, if I wouldn't have put it up here, I would have said, are those really far apart? You go, yeah, it's 1 billion apart, damn. But the standard deviation is 1 billion. On average, data points are this far apart from the mean. So these are not very far apart based on that. Now, if the standard deviation was instead 500,000 or something, now these are really far apart, right? Because on average, the data doesn't get more than 500,000 away from the mean. These are 1 billion apart. Holy crap, that's huge. Okay. So one little thing I want to get to, before we get into the real conceptual stuff here, is the idea of a z-score again. I talked a little bit about that in the day of review, but I want to come back to it. And you guys, I think we did this exercise. Let's say that this one is the mean. 5 billion is the mean. You just put 5. You know it's 5 billion. And here's 4 billion. Now how many standard deviations away from 5 billion is 4 billion, given the standard deviation of 500,000? Maybe something like that. How can you find out for sure? How far apart are they, period? 1 apart, right? And every step is 500,000 big. So these are not 1 apart, you care, it's 1 billion. How do you write 1 billion? So I got 4 billion minus 5 billion over 500,000. That's the z-score. So if I see how far apart are they, period, how big is each step I take relative to the data, and divide those, it'll tell me how many steps there are in between these two. That tells me how far apart they are. That's how we measure distance in statistics. Z-scores are a measure of distance. Now, they're allowed to be negative and positive, and normally we don't think distances can be negative, but what is a negative tell me? It's below the mean. Beautiful. So in a test, you don't want to have a big negative Z-score. That'd be you're really far below the mean. In golf, you want a big negative Z-score. This is lower scores better. So what do you guys get for that if you do that?
2,000.
2,000? So 1, 2, 3, 4, 5. So maybe 5. Yeah, 50,000, 40,000 by 50,000. Negative 10,000 divided by 5, negative 2,000. Cool. Okay. So, how many times more are these two apart than the average distance that things are from the mean? 2,000 times as much. You with me? So on average, data here, so really my picture's kind of wrong, and I didn't know where to put this at first. But where is that 4 billion really in relation to the mean? Way the hell. In fact, it's stupid far down. And there it is. You guys with me? So the data, if the standard deviation really is just 500,000, then I would expect, like here would be 5,500,000. You with me? I guess I could write it as an actual number, Jeff. You can. That would be 5,500,000. That's how little it changes. So most things are very close to 5 billion because it only changes by 500,000. So the data is kind of tight. These big ass numbers, but they don't change that much. How we doing so far? Okay, semi-decent. So when is this going to become useful? I keep trying to interject little things that is going to come up much more important, like in chapter 8. But I can talk about them right now. Why is this useful? If somebody makes a claim, I claim that 70% of gross fund students smoke, or something. And I find data, I take a sample, and I find something that's so far away. Okay, how do I measure distance? Z-scores. Kind of with me? So chapter 8 is going to be all about somebody makes a claim. I test this claim by doing what? Going and taking a sample. I claim that my drug will, on average, have your headache go away in 5 minutes. All right, well, let me take a group of people, give them the drug, see how long it takes, and see how far away from your claim that is. If I do a group of people that takes them 20 minutes, that might be pretty far away. Right there. If your claim is 5 minutes, and I find a group, and that takes them 20 minutes, here's where it's a little weird. Is that enough evidence by itself to say that your claim is wrong? No. What am I missing? I love it. Standard deviation. Right? If the standard deviation is 1 minute, is that far away from this? Hell yeah. If the standard deviation is 15 minutes, that's just one step away. It wouldn't be that unusual. Are you guys semi with me? So if your claim was right, let's say the standard deviation is 1 minute, and your claim is right, what's the possibility that it just happened to get a bunch of people that the medicine doesn't really work for, and they came out to be this long? Very low odds, very low probability. What's more likely? Your medicine ain't that good. Sorry, buddy. You tested on rats, worked great. The rat said, oh yeah, I feel better. Yeah. I don't know how they'd see that. Obviously, I'm not a clinician. If it was 1 minute, this would be really good evidence that your medicine sucks. Sorry, buddy. Medicine takes way longer than you claimed, right? But if the standard deviation, so this would be sucks. Evidence against you. Because, exactly why? That is so far away from what you claimed it should be. Okay, cool. Although, if my standard deviation was 15 minutes, that's not evidence that your medicine sucks. Be careful, it's not evidence that your medicine is good. You can never prove something with a single instance. But it's not enough evidence to say that your medicine sucks. Okay, hoping you guys are semi with me. I just want to give you a little preview. There's a lot of math behind this, obviously. We're going to see all of it in chapter 8. But this is one of the most important things in statistics that you can use z-scores for. Telling how far apart things are so you can kind of test a claim.
In polls, how come they don't use standard deviation to show if there's like
Where?
a large, like when they do national polls of, you know, people approve of this or don't approve.
They do. Where do you think the standard deviation shows up? When they
Oh, is
say
that the plus or minus?
Obama, exactly. Obama, 49%. Romney, what is he at, like 45% right now?
Yeah, and then it's like plus or minus.
And then they got the little Paul supporters. Come on, damn it! 4% or whatever. Yeah, at the very bottom, plus or minus 4. I've been seeing 4 a lot more than 3 now. Standard deviation is a part of this part of the equation. It's not the only thing, but the standard deviation is definitely a huge part of this. Right?
So that's what
If the
that
standard
is.
deviation was smaller, this number would be smaller because it'd be more sure about what I see. If the standard deviation is really big, I'm not that sure about what I see. This is going to be bigger to cover my ass. Okay, so that's a good point. That's where it shows up.
That's that.
So they do use it. Yes.
On the same thing, I remember this sticking in because I was so confused. I had no idea what they were talking about. They had 2 things. I think it was like a presidential thing. I don't know if it was this year or last time or whatever. But one person had like 51, and the other person had like 52, and I was really confused. How did they do that?
Because if it's 51% versus 52%, of course that adds up to more than 100. You're like, are 3% of Canadians voting in our election? Hey, come on. If the margin of error is what it's called, if that's plus or minus 3%, this could be anywhere from 48 to 54. You with me? And this could be anywhere from 49 to 55. You with me? Now this doesn't happen that often because they're claiming that their best guess is this. And you're like, you don't want to admit that your best guess adds up to more than 100%. What this would probably mean is their margin of error is large. I would say it'd be like 6 in this case, because that means they're really not that sure about what they saw if it adds up to more than 100. But it's probably, you saw that somewhere?
Yeah.
Why would they cut them both down by 1.5%?
Say again?
Why wouldn't they cut them both down by 1.5%?
Because then they're lying. If they really saw this from their samples, if they saw this, and I want you to be really careful. I mean, if they see this from some sample they took, number one, this is weird, because I honestly don't know how they could exactly get this. It depends on the way they worded their question, right? But if you change them at all, you're lying. You give this and you admit that there's a margin of error because that's life. You're not sure about what you saw.
Could it be a rounding issue?
Sometimes it could be a rounding. In this case, I wouldn't say this, but if I had like 51% and 50%, I might say it's a rounding issue possibly. Like this was 50.5 and this was 49.5. With me, those add up to 100. If you round them both up, it looks like you're over. Anyway, okay. Like. So let's see, with all that in your heads, hopefully, let's talk about, let me actually let you guys try a couple things out. Let's say the mean of something, here's an X here. The mean of something is 129.3. And the standard deviation is 18.1. 0, 0. So it's been right. What's the z-score for these data points? So take a second and do that. That's my catchphrase. Take a second, do that. And what I like about this, it's very subtle what's going on here. What's the only thing you know about my data? There's two things, the mean and the standard deviation. And I try to make the point that if I knew the center and how spread out on average the data is, that's an awesome summary. Do I really have to give you the whole list of data then? Only if you want to do other things with it, but these two things by themselves give me a lot of information. So on average, things are at most that far away from this. Doesn't mean it's impossible that one of my data points is 2,000, as long as all the other data points are pretty damn close to this. You with me? So there could be an outlier, but what does that mean about my other data points? They must be relatively closer, so that overall the average doesn't get over 18.1. Maybe. So what do you guys get for this here?
Negative.
So it's always our data point minus the mean divided by standard deviation. So it's our data point minus the mean divided by 18.1. So I'm sorry, say it again.
-1.
-1, cool. That's what I was going for that one. So is that relatively far away from the mean? No. I like it.
How many decimal points do we need for the z-score?
I'll tell you this, it's gonna be 2, and it'll make a lot more sense when we get to chapter 6, because there's a chart we're gonna be using out of the book that only goes out to 2 places for the z-score, so if you round it to more than that right now, it's fine. But for z-scores, we'll go 2 places. That was exactly -1, so we're good there. Can somebody describe that to me then, that data point is,
normal, smaller.
well, it's within expected limits, that's one way to say it.
It's less.
Be more specific about this number.
How did you get the number?
Good.
Oh, I'm glad you said that. When you plug this in your calculator, you've got to include that. You with me? If you don't include those, what is it about this problem that tells us, as the humans, that what order I have to do things in? The big ass division sign, right? Now when you put it in the calculator, it's going to see this. It knows order operations.
Oh, never mind.
It knows, please excuse my dumbass son, or dear son. But what is it supposed to do first? It's supposed to do that subtraction, so I have to throw those parentheses in. Those parentheses take the place of the big ass division sign. Okay, cool. It's one of the most simplest mistakes I see all the time. We know that that's not very far away. This should not be very far away from that. So if you come out with a z-score of, what would it be here? 20, like 100 something, right? 102.3 or whatever the hell it was. That's a little crazy. You're saying you're 100 steps away from, no, I'm nowhere near 100 steps away from that. That doesn't make any sense. Okay. So what about part B?
2.691. 2.691.
2.691? Okay, cool.
You want us to round 3 places for these?
Well, it'll be 2. It's okay for more right now. Later, we'll be forced to use 2 because the chart is only going to go out to 2 places. So 2691 is beautiful right now. What do you say about that data point then?
It's 2.7.
2.6.
Yeah, it's more than 2.5 steps away from the mean. That's starting to get to be kind of unusual, wouldn't you say? Right? That's getting to be unusually large. Like if this was, what makes sense here? An average weight for, I don't know, jockeys. And if I had a nearly 180 pound jockey, that poor horse. That's unusual. It would be. I don't know. You with me? I'm not, obviously I haven't
That might
looked
be
up
how-
jockeys'
That
average
might be
weight.
how much they weigh.
Whatever this data is, if this is truly the mean and this is the standard deviation, that would be an unusual value. Because what usually happens, they're close to this. Usually they're that far away from it on average. Okay? Maybe, yes.
So the z-score is how many steps away from the mean the data point is?
It's how many steps away from this that the data point is. That is a measure of distance.
Right.
So just like in real life, I could use inches, or I could use centimeters, or I could use miles. In statistics, we always use standard deviation. It changes based on the data, so it's sort of like it's saying centimeters here, miles there. I'm hoping. Always hoping. So this is my ruler markings, and this is when I lay the ruler down, and I measure. How many of these are in between this and this? That many. Take a measurement, right? Don't worry, I'm hoping that some of you guys are a little bit worried about what z-score would make it unusual. I'm getting to that here in a minute. Yeah.
How do you do it when it's not like a numerical value, when it's like, you know, this many people like Barack Obama or don't like him?
That's still
How do
a
you find
number.
out plus or minus?
Yeah, so it's a good
Like-
point you're kind of making.
it
Obviously,
like-
a z-score could only be used on quantitative data,
Right.
because
Is
you
it
can
like-
only do an average for
Do they
quantitative.
assign a value to like level of approval, like strongly approve and like that,
You
or?
possibly could, but no.
No, okay,
Normally, you can't force ordinal to act like numbers.
okay.
And in fact, I don't know if I want to get into that. Like, I could take an average hair color, even if I assign numbers to 0 for bald, 1 for very blonde, 10 for black hair. You with me? That's me imposing numbers on a situation. It won't mean anything if I take an average. Yeah.
But don't they just add up the votes? And it's like, alright, 50-something%. And
You can do percentages, sure. Percentages, what kind of data can you use percentages for? Any.
yeah.
Yeah, qualitative. I've used them for car types, right? 20% out of BMW.
How do they do like the plus or minus for, that?
Chapter 7.
Okay.
Way too far ahead for us right now.
That was.
All right, I like that fact that some of you guys want to be in chapter 7. Let's not go there yet. And then finally, this guy. What do you get from him?
Negative 2.73.
What was this?
Negative 2,
2.72?
724.
Cool. So this is unusually large of a value. That's unusually small of a value. All right, so you got a very tiny dude up there. The horse is like, are you even there? Oh, yeah. All right, so that's the nuts and bolts of just calculating z-scores, right? And I think I had that kind of problem on the practice test. Remember, and I said that wasn't going to be on this next test. Exactly this kind of problem. So you can see I'm going to have exactly that kind of problem on the next test. So unusual, real quick, unusual values. In order to figure this out, we have to do a little bit of back work here. So there's a couple things we're going to talk about. The first one is important to get us going, but I'm not going to make you memorize anything about it. The second one is stupid important. You're going to have to memorize everything about it. It's only going to be 3 things, so don't forget. So the first thing here is Chevyshev's theorem, or what I call Chevy. Chevyshev. I have no idea if he was chubby or not. Chevyshev's, yeah. Now, I can't get into the super specifics, but it should make sense roughly why his theorem works. So his theorem works for any distribution. Which I'm hoping, when I'm done talking about Chevyshev's theorem, I'm hoping some of you guys go, holy shit, so any set of numbers I make, this is true. Any freaking set of numbers you make, I don't care what numbers you make. Make them pi, make them square root of 87, make them negative 14 billion, I don't care. This will be true for it. To me, that's kind of awesome. So Chevyshev's, let me just make up some data that I always do the same thing, just because. But let's say I have data like this. And really just make sure we all understand what this is. It's me walking around, let's say these are ages of people somewhere. Ages on some island somewhere. I normally say Florida, but people know they're at people. Why is there such a big gap here on this island then? So if I walk around and say, how old are you? I'm 1 year old. Okay, I put you there. How old are you? Hey, Sept. Okay, I put you over. Right, so I'm putting little dots down. So I'm sort of making a dot plot in a way, really. And it kind of builds up and I end up with this. What's happening here?
War.
There's no people in there. It's either only younger people or older people. So now you see why I was talking about Florida, because Florida you have Boca del Rey, shuffleboard, Okay. And then you have, obviously you have younger people in that. This isn't quite true, there's nobody. So the average would be about where?
In the middle.
Yeah. Boop. Okay, so far so good? Now again, Chebyshev's is true for any distribution. I'm just picking this one to be kind of an extreme example. But it works for anything. If I go one step up, let me start throwing some notation at you. If I go one step up, okay, let me just write that. Can you guys see that? Is that cool? Because if I take one step up for the mean, what do? I take the mean number and I add a standard deviation. So there you go. And if I take one step down, it'll be
You subtract.
mu minus. Okay, how are we doing so far? Underneath this, let me put the number that's the z-score. What would the z-score be for this? 1. I love it because it's one step away. Don't make too much out of that. And what's the z-score for this guy?
-1.
And what's the z-score for this guy?
0.
Because he's 0 away from himself. I love it. Sweet. How much of the data might I collect if I take one step up and one step down?
3.
I might collect nothing. Now we saw an example earlier. Remember when I had up here 1, 5, 3, 9, 10? Remember we did this? And we did, I think the mean was 5.6. And we ended up catching 60% of the data, didn't we?
Yeah.
What Chebyshev said is you could have such a freaky ass distribution that you take one step up and down and you don't catch a damn thing. So the first step of Chebyshev's theorem is kind of lame. And I just admit that up front. Chebyshev says within one standard deviation of the mean, there's at least 0% of the data. And you're like, way to take a chance. What'd you say? How many people in here do you think like that show? Well, I got at least 0%. Okay. Interesting. You guys with me? So that's sort of lame. But it's got to work for every freaking possible distribution, so we give him that one. We give him a little mulligan now, that's fine. I use all this golf stuff. I don't even play golf. If I go out one more step, though, now I'm hoping some of you guys are going to argue, well, that's just the way you're drawing this shit, Jeff. If I take one more step out, I'm going to catch some stuff, am I not? At least according to my picture that I've drawn so that it will happen. And you might say, well, Jeff, what if I'm God and I just reach down in this island, or whatever deity you enjoy, the spaghetti monster reaches down there and he says, I'm going to take all of you people, make you older. You're like, oh shit. So they go up here. And you people are younger. Some of you are not even born anymore. So I'm trying to escape. I'm trying to escape the standard deviation stepping out to catch me. But the minute I do that, what's going to happen?
The standard deviation will adjust.
Standard deviation gets bigger. You cannot escape the standard deviation. That's the key of Chebyshev's theorem. If you take one step, sure, you might escape. You might be a bunch of stuff up there and a bunch of stuff down there, so you might not have anything in the middle. But 2 steps, I will always catch at least. Now here's where it gets a lot less lame. Within 2 steps, there's at least 75% of the data. Now, I want you to stop and just think about this. You sit down and you write down a list of any numbers you want. I don't care what numbers you pick. I do not care. You calculate the mean and the standard deviation, and you take 2 steps up and down. You will catch at least 3/4 of the data. I'm hoping some of you guys are going, all right, that's interesting, math dude. I'm hoping it's vaguely interesting to somebody who's not as into math as I am, obviously, right? That's kind of freaky. Any list of data you want to make, I don't care what numbers you make, this is true. A lot less lame than statement number 1 was. And then I can imagine if I take one more step out, so this is mu plus 2 sigma, right? 2 steps up, 2 steps down. Take one more step down, one more step up,
Because I'm huge.
and now it's going to be
More than
within 3, there's at least 89% of the data. Okay. But what was the centerpiece of this? If I try to escape, I change my standard deviation. If I try to do the other way, if I try to smush everybody into one, smush in there into one. Well, now the standard deviation is a lot smaller. They're not all going to fit into one. That's the centerpiece. Can I tell you exactly why he got these numbers? No, the math there is a little more advanced. At least the center idea makes sense. So,
At 4, do you catch all of them?
no, you never catch all of them, right? It's like this never-ending Pokemon game. Pokemon's come up. Because theoretically, this could go forever. Now, if this is ages, there's obviously a 0, right? There's nobody who's negative here, so you can say negative 9 months old, I guess, we just can see. But kind of with me. But theoretically, this goes up forever too. Theoretically. So you actually can never catch them all. If you go up to 4, it would be 15 16ths. What's 15 divided by 16? 90, 0.9? 0.937? Cool. All right, so forth. Little, I don't want to get into the formula. There's a little formula you can read about in the book if you want to. K is the number of steps you want to take. So real quick, if I took 2 steps, what's 1 minus 1 over 2 squared? 1 minus 1/4 is 3/4, 75%. 3 steps, 1 minus 1/9 is 8/9. 8 divided by 9, believe it or not, is 88.8888, so 89%. Cool. That's his little formula that he came up with. I'm not going to make you memorize that. Okay. All right. Oh, wow. That sucks. The other big one was the empirical rule. Let me say this, by the way. I think next time I'm going to work on an updated timeline. So obviously, I've allowed us to get a little bit behind my original schedule. And that's why I put the words tentative time frame up there, because I knew that might happen. So I'm going to give you an updated homework sheet timeline with some updated dates. The empirical rule only applies to normal distributions. Stay with me now. So, a big chunk of statistics is all about how can I show that something is normal enough to use this? Right, and we'll see that later. We'll see how can I show this is obviously not normal, is it? Why not? Because it doesn't go up and come back down, and that's it. It goes up and down and up and down and up.
There's
That's not
0
normal.
people between the age of
And there's nobody in there. It should be the opposite way. It should be most people in there, right? So this only applies to this kind of distribution, like bell curve. So there's a lot more precise. There's a lot more that I know. So it should be a lot less vague. It shouldn't have any of this at least crap. And there's no way it's going to be 0% here, is it? Because like we just said, most of the data has to be in the middle for a normal distribution. So for this guy, if I go up or down, let me just cut to the chase on this one. Is that all right? That's 0. This is 1, -1. Is that cool?
Yeah.
You guys cool with that? Do whatever you want to. Stats boy. Just do it. All right. Within 1 step of the mean. Some of you guys already know this number because you've read ahead. Within 1 step of the mean, within 1 standard deviation, there is 68%. Now, to be completely honest, that is rounded. It's 68.28 or whatever the hell it is. But we're going to call it 68%. Okay? So it's a definite number. It's not at least. If you have a normal distribution, there is 68% in there, period. End of story. So a really powerful thing there is, I know that heights of people are normally distributed. So if I had to design a door, for example, so that only a certain percentage of people, if I'm up here, what might happen to me in a doorway if I'm not careful? Hit your head. So I can design a door to be so tall so that only a certain percentage of people will have to duck. You with me? Or airplane seats. I always like to do this because there's a big article a while back about all of our widths are getting wider. So they want only a certain percentage of people to have to buy a second seat or something. Oh, you still with me. So they have to know the average girth And the standard deviation to see, well, if I want this percentage, how big do I have to make that seat? So only this percentage of people will come and complain to me. I'm desperately trying to give you real life stuff that are using something, we're almost there, we're almost to the point to do that ourselves. That's the kick-ass thing about stats. We're almost to the point where we can do a study like this ourselves. How tall should our door be? How wide should the seats be? How many seats should I book on a plane, given the average number of people that don't show? And the standard deviation, don't they overbook planes all the damn time? And the reason they do this is because they want it to be full, and if it's not full, then screw you. No. Or, if it's over full, really. So they do that because they know that a certain percentage of people, and there's only a certain percentage of the time they're going to have a lot of people angry at them. So they'd rather make more money and deal with angry people than to not make much money and have everybody be happy. You with me? Okay. Just to finish this out, I know it's time. Within 2, there'll be 95% of the data. And within 3, bless you, there's 99.7%. You still never catch all the data, theoretically. If I'm talking about heights of people, obviously, and that's the thing with math. Math is always ideal case. In the real world, nobody is an inch tall, and nobody is 50 feet tall. So at some point, we've caught everybody. But this works really well for the middle stuff. So coming back real quick, last thing, remember the first that got me into this was unusual values? So we officially call anything outside of 2 steps away unusual, because how much stuff is out there? How much stuff is outside of 2 steps away?
5%.
5%. There's 95% inside, so how much is outside? 5%. So that's pretty damn unusual. So we officially call unusual values anything outside of 2 steps away. Sweet. That's enough for today. Thanks. Thanks, man.